Hello everyone, welcome to the another session of digital signal processing. We have been discussing about fast Fourier transform from the last few sessions. Today we'll be discussing about inverse fast Fourier transform. So the algorithm that we're going to use to calculate the inverse of discrete Fourier transform, that would be same as we have discussed in the last session, that is fast Fourier transform using the butterfly diagram. So here what do we see, that whenever we are calculating this particular value inverse, that is xk, using the sample value xn, I'm going to use the process which is opposite of calculating of DIT. So we had two algorithms, DIT and DIF, and we had seen that in this DIF algorithm, I'm starting from the frequency domain, decomposing the sequence and coming back into this xn sample values. So in the case when I'm calculating the xk, this is going to be the preferred algorithm, that is the butterfly diagram, in which we create the stage 3 first, followed by second and the first stage. Those diagrams would be used for calculating the inverse DFT using FFT. So what two different things we have to consider while calculating IDFT using the same algorithm that we were using for calculating the DFT. First thing is, there would be inclusion of one parameter, that is 1 by n. Secondly, the factor which is the complex conjugate of the Twiddle factor that we were using in the DFT. So what that means and where these two factors have come from. When I talk about the definition of DFT, I simply talk about it is xn e raised to the power minus j 2 pi by n kn. For finite sequences, this range from 0 to n minus 1. And this k also ranges from 0 to n minus 1. Now let me write the definition for this inverse DFT, that is x of k. This is 1 by n summation, let me correct it here, x of k and x of n. This is x of k and this exponential is positive, j 2 pi by n kn, where this k was summated from 0 to n minus 1 and here n was ranging from 0 to n minus 1. So if we compare these two things, definition of DFT and definition of IDFT, what do I see? Here, this is xn, input sequence is xn, input sequence is xk. This factor has the negative power and this factor has a positive power. This entire summation is multiplied with 1. But this entire summation is scaled by factor n, where n is the number of samples into the given sequence. So these two factors would be depicted into the graph also. That final answer that I'll be obtaining would be scaled down by a factor n, and the Twiddle factor that I am going to use here, it was positive values of nk. Here I have to use the negative values of the Twiddle factor. So first of all, I must know what are the Twiddle factor or conjugate Twiddle factors for different values of n. So mostly we are discussing a graph for 4-point and 8-point FFTs. So I must know the values of Twiddle factor for different values for the conjugate part for this. So these are the two differences which are coming directly from the definition of DFT and IDFT that will be incorporating into the graph of the IDFT. So if we multiply entire result with 1 by n and replace the Twiddle factor with its complex conjugate in DIF algorithm, the butterfly diagram that we have created, we can get the IDFT using the same method that we were using for calculating the direct FFT algorithm. So first of all, I know when I need to divide the answer by n, I know the value of n, I can scale down the answers. But how to calculate the value of the conjugate Twiddle factor? So these are the values which are used in the calculation of DFT, and these are the values which are used in the calculation of IDFT. So what are the different, can I say? The power of W is all positive here. The power of W's is negative here, showing that these are the conjugate to each other. If I see these values, this and this value is same. But in this value, what do I see? 0.707 minus 0.707j. And here this real part is same and sign of this part is changing from negative to positive. Similarly, here it was negative, it is positive. Minus 1 is the real part, remains the same. Look at the second part of every value. That is the negative of the one in the DFT. J has become minus j. Plus 0.707j has become minus 0.707j. One remains the same. So from this comparison, what can I conclude? That calculating the complex conjugate of Twiddle factor is just invert the sign of complex part of the non-conjugate value. These are my non-conjugate values and these are the complex part. So by changing the sign, inverting the sign of the complex part of this non-conjugate Twiddle factor, I can calculate the value of the conjugate part of the Twiddle factor. So that means I have to use all these values of the Twiddle factor once I start weighing my FFT diagram for every stage of decimation. So look at this diagram. This more or less seems like my DIF algorithm diagram which we created for calculating the DFT or FFT. What do I see here? All the input samples are now xk and output samples are xn because I am calculating the inverse. This is my first stage now, this is my second stage and this is my third stage. The same. I see that minus 1 have been weighted to the lower part. Here also and alternatively here, no difference. W is coming after the multiplication part in every stage. So where lies the difference? Difference is W is negative here at every part and every stage. And in the last stage, I can see once this complete calculation has been completed, everywhere I have multiplied the answers by 1 by 8. So in entire graph of DIF, I am seeing two differences, conjugate Twiddle factors and scaling of the output by 1 by 8 because here n is 8. If same graph is being plotted for n is equal to 4, this scaling would be by 4. Third difference what I see, here I am inputting the capital X case and output is xn. So these three differences are there between the DIF algorithm which I am using for calculating the Fourier transform and the same algorithm used for calculating the inverse Fourier transform. So how do I see it here? Let us solve for 4-point FFT algorithm and I need to verify the results for this. So what is this? This is my xk. And from this xk, I need to create xn. So what I have to do? I have to create this butterfly diagram, that is DIF IDFT diagram. So input would be ordered. So input is 6, minus 2 plus 2j, minus 2, minus 2, minus 2j. So I have given them in the ordered way. These are my first stage. This is my second stage because n is equal to 4. So I have only 2 stages of decimation. In the first stage, what I am seeing, this is 6 and this is minus 2. So 6 minus 2 is 4. There is no weight. So 4 would become input to the next stage. If I look over here, minus 2 multiplied by minus 1, that is 2. And from above, what is coming? 6 plus 6. This is 8. 8 is now being multiplied by W minus 0, 4. This is 1. So say 8 multiplied by 1, input is 1. If I look at this sample, minus 2 minus 2j multiplied by minus 1, it has become positive, that is 2 plus 2j. And from here, what I am getting? Minus 2 plus 2j. So 2 plus 2j, and from above what I am getting? Minus 2 plus 2j, that is 4j. These would cancel out, I am getting 4j. And this 4j would be weighted by this value, that is W minus 1, which is j. So if I multiply this with j, this is minus 4. So this minus 4 become input to the second stage. Similarly, I will solve for this 2-point DFT and calculate the answers. So answer I am getting is 0, 8, 4 and 12. This has to be scaled down by 4 because n is equal to 4. So this comes out to be 0, 2, 1 and 3. And look, these are unordered, x0, x2, x1 and x3. So my final answer, I write issued in the ordered way. So answer is 0, 1, 2 and 3. I can verify this result. I can take the FFT of this point. The output would be this. So this is a self-check algorithm in which we can decide on that whether this calculation is correct or not by drawing the graph again and calculating the FFT in the normal direction. The same graph can be solved for the 8-point FFT also. I need to calculate xn and given is xk. So this is how the graph appears. I am giving all the samples in the ordered way, calculating all the point stage by stage. Whatever output I am getting after calculating 3-stage diagram, I would scale the output by 8 at every stage. And finally, I get these answers. These answers are unordered, 0, 4, 2, 6, 1, 5, 3, 7. So we'll arrange them in the form of ordered way and receive the xn corresponding to this given xk. So more or less, complete DIF FFT is being used for calculating the inverse of the given function just by making changes of the Twiddle factor. Rather than using the non-conjugate part, I'm using the conjugate part. I'm simply scaling down the answers by the number of samples given into the input sequence. Two other things which I can conclude about all of these diagrams may be DIT butterfly diagrams or DIF diagrams is the bit reversal. Bit reversal is basically whenever I write something like 1, 0, 0. So I look at this first point and this last point and I create a sequence like 0, 0, 1. So I have only swapped the places 1 and 0. So this sequence which I have created by swapping the LSB and MSB of the given sequence, this is called as bit reversed. So this is just like reversing the bit in a binary word from left to right. Therefore, the MSBs and LSB, they get swapped. MSB become LSB and LSB become MSB. So whenever we are performing this DIT, we have seen that we are giving input in unordered way. In DIF, I am obtaining output in unordered way. And if I try to see the pattern of this unordering, I would see that unordering is nothing but these unordering is following the bit reversal pattern. So this bit reversal, these are trivial when we implement them in the hardware, and because of this we get many advantages, first in the calculation and second into the memory which is required for the calculation. So in DSP processors, what we do, we include a special hardware for performing this bit reversing and indexing capability, and which is one of the things which distinguishes my DSP processor from the microprocessor, a general purpose microprocessor. So looking at the few examples, if I'm talking about 8-point DFT, if all these are binary indexing which I am using, and these are corresponding bit reverse indexing corresponding to every stage. If it is 0, 0, 0 and I reverse or swap the LSB and MSB, the pattern remains same. For this, if I swap 0 and 1, this becomes 1, 0, 0. This remains the same. For this, if I swap 0 and 1, this becomes 1, 1, 0. 100 becomes 0, 0, 1. This remains same. 1, 1, 0 becomes 0, 1, 1. So what do I see? If this is 0, 1, 2, 3, 4, 5, 6, 7, this is 0, 4, 2, 6, 1, 5, 3, 7. So after performing the bit reversal operation, the pattern gets changed in this way. And this is the sequence to which we were talking about unordered sequence in DIT algorithm as well as DIS algorithm. So that means when we create this butterfly diagram, this is certain to happen. In DIT, this would appear into the input side. In DIF, this is going to appear into the output side. So this has been deliberately done. And what is the advantage that I get because of this bit reversal? It is we can perform computation in place. Computation in place is basically corresponding to the memory requirement. How much memory do I require when I start calculating the FFT using this butterfly diagram? So this in place actually means the FFT that is calculated entirely inside the original sample memory. So if I have taken say 8 memory slots, then these 8 memory slots would be repetitively used in every stage. That means if I am using these 8 memory blocks M1 to M8 for calculating the values of stage 1, then answers which I'll get for stage 2 would be overwritten into these memory itself. So I do not require a new set of memory. I can overwrite my previous answers into the previous memory itself, and I do not lose any information. So it is important to note that if input signal data are placed in bit reverse order before I start calculating this FFT, the output of butterfly at every stage throughout the computation that can be placed into the same memory location from which the inputs were fetched, resulting in place algorithm that requires no extra memory to perform the FFT. So most of the FFT implementations that we have, they are in place. So we can overwrite the input data with the intermediate values and finally the output. So using this butterfly diagram, in short, I am trying to save the memory. So this unordering of the sequence at the input or receiving the unordered sequence at the output has the advantage of saving the memory. So I can conclude that when I am using this FFT algorithm, two advantages are here. First, I am reducing the computation complexity, fewer number of multiplication, additions and solving of trigonometrical functions, that is reduced to a very, very large scale at a logarithmic scale. And second advantage which I am getting along with this is the memory requirement is reduced, because using this butterfly diagram, I can calculate or I can perform in-place computation by exploiting the bit reversal property. So overall, when I am implementing these butterfly diagrams or any kind of FFT algorithm, I am saving a lot. So that is the advantage, that we are learning so many diagrams which look to be complex, but ultimately when I implement it into the hardware, I am saving a lot of memory and lot of time in the computation. That's all about the DFT. Now we'll see some of the applications of sampling as multi-rate signal processing. That is an entire different area of discussion. So we'll be discussing this multi-rate signal processing into the coming session. So we are done with this session. Thank you.